Good morning, all of you. My name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education to all. For that purpose, I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today we're going to discuss about sampling. So these are the outlines of today's lecture. We'll start up with the introduction. Then we will give the statement what is sampling theorem. Then we'll discuss several sampling methods, in which we discuss about ideal sampling method, natural sampling method, and the flat top sampling method with all its necessary mathematical details. Then we'll briefly discuss about how we're going to reconstruct our sampled signal. Obviously we'll not going to go into greater details about several reconstructions method, likewise our interpolation method or zero hold method, but we'll give a brief overview how with the help of low pass filter we're going to reconstruct our message signal back from the available frequency spectrum. Then we'll discuss the aliasing effect, and finally we're going to conclude. So here is the introduction. Most of the signals that we use in our daily life are generally analog in nature. For example, as we are talking to each other, weather signals, temperature signals, etc. These are all our continuous time signals. Digital systems possess many advantages in comparison to analog systems, such as they are immune to noise, it can be stored, processed with more efficient algorithms, they are secure, they are much robust as well as cost effective due to the advancement in our VLSI technology. So obviously these are several sorts of advantages which possess our digital systems in comparison to our analog systems. So most of the effective signal processors are digital signal processors, such as nowadays we are actually utilizing computers to process our data, which are digital in nature. So digital signal processing is having much more advantages in comparison to analog signal processing, as we mentioned some of the points above. So most of the effective signal processors are digital processors which needs digital information in order to process it. Then the question is, since most of the signal sources are generating analog signals, then how are we going to convert it into the digital information so that we could process it with the help of digital signal processors? So hence there arises a need to convert our analog signals to the discrete time signal in order to process them properly through the digital signal processors, and then further again reconvert them back to the analog signal so that we can understand them. Obviously we could not understand digital signals. Sampling is the answer to that particular need. Sampling is basically a way by which we can convert our continuous time signal into the discrete time signal. The sampling theorem states that a band limited continuous time signal can be represented by its samples, and it can be recovered back when the sampling frequency, which is your fs, is greater than or equal to the twice of the highest frequency component of the message signal. That is, sampling frequency should be greater than or equal to twice of fm, where fm is the maximum frequency component of the continuous time signal. So here the keywords are band limited as well as sampling frequency. So what do you mean by a band limited signal? A band limited signal is the signal which we can say that it is possessing some maximum frequency component. Beyond that frequency component, it is not going to possess any frequency component. All the frequency component possessed by that particular signal will be less than that maximum frequency component of the signal. Then sampling frequency. What is sampling frequency? Sampling frequency, basically the frequency or the number of samples that we're going to take per unit time, and which will be greater than or equal to twice of the maximum frequency component of the signal if we want to recover our message signal back properly. So we could obviously say, suppose the maximum frequency component of any continuous time signal is 10 Hz, then sampling frequency should be 20 or more than 20. It means number of samples per unit time that we have to take to reconstruct that signal back should be 20 or more than 20. So this particular figure specifies the generalized method of sampling. what theoretically we perform in our sampling. So obviously we're going to have a continuous time signal, which is your analog signal represented by this xt. Then it is the product of that analog signal and a particular pulse pt, which is also known as our sampling function. So with the help of multiplier, we're going to have the product of these two signals, and the outcome of that signal will be a discrete time signal, which is represented as the sampled version of s, that is equal to x of nts, which is your discrete time signal. So analog signal is being sampled every ts second, where ts is the sampling interval, and f of s is equal to 1 by ts. Obviously sampling interval is the inverse of our sampling frequency, which is called the sampling rate or sampling frequency of the signal. Then sampling method. There are basically three types of sampling methods. Number one is your ideal sampling, which is an impulse at each sampling instant with amplitude equals to the signal at that point of time. This particular figure represents that thing. We're going to have a continuous time signal like this one. Then when we're going to apply this impulse train, which is shown by this pink color, both of them will get multiplied, and the outcome will be a series of impulse trains like this one, this one, this one, and this one, whose amplitude is the instantaneous amplitude of that particular signal. Then second method of sampling is our natural sampling. Natural sampling shows by this particular figure. Here we can see that a pulse of short width with varying amplitude. This is our amplitude variation. This is amplitude variation. This is amplitude variation. Obviously we're going to have a pulse which will get multiplied with our continuous time signal, and it will going to take the amplitude of the instantaneous message signal. Then third one is our flat top sampling, which generally make use of sample and hold circuitry. It is almost like our natural sampling, but with a single amplitude value. This particular figure shows that the top of the signal is a flat one, this one, whereas in the natural frequency will be not having these flats top, they are varying, but in this particular sampling method we'll be getting flat top. What are the advantages associated with it? We'll simply discuss when we'll try to get the concepts about flat top. So now what is impulse sampling? How are we going to perform impulse sampling? So impulse sampling can be performed by multiplying our input signal xt with the impulse train pt, which is nothing but your sampling function of the period ts. So pt has been described by this particular figure, delta of t minus nts, where n starts from minus infinity to infinity. So here the amplitude of the impulse changes with respect to the amplitude of the input signal xt. What we're going to do that? We'll be having this particular signal xt, which is nothing but your continuous time signal. It is get multiplied with the sampling function or impulse train pt. Impulse train is periodic with the period of ts, or after every ts second we'll be having an impulse signal. So both these signals xt as well as pt will get multiplied with each other, and we'll get this time varying impulses whose strength is equal to the instantaneous value of our analog signal, and these impulse trains is your impulse sampled output. So the output of the sampler is simply being given as xs of t is equal to xt into pt, where xs represents the sampled version of the signal, which is equal to the product of input signal and the sampling function. So what is this sampling function? We had said that it is your impulse train, which is represented by delta of nts, and starts from minus infinity to infinity. So now recall the shifting property of the impulse function, which states that xt delta of t minus t naught will be equal to x of t naught delta of t minus t naught. It means the product of xt and delta of t minus t naught will get the outcome value of x at that particular instant, that is your xt naught, with the product of delta of t minus t naught. So using same property, what we're going to have, sampled version of xs of t, which is also being represented as x delta of t, where this delta actually representing that we are taking impulse sampling, equal to summation of n starts from minus infinity to infinity x of nts delta of t minus nts. So as a t naught we are using nts, so we'll get this outcome, and let us say this is our equation number 1. So to take the spectrum of the sampled signal, let us take the Fourier transform of equation 1. As we know, the multiplication in time domain becomes the convolution in the frequency domain. So what we're going to have right now is xs of omega. Obviously it is representing the Fourier transform of xs of t, which is equal to x delta of omega, which is nothing but the Fourier transform of x delta of t, that is equal to 1 by 2 pi convolution of x of omega with p of omega, where x of omega and p of omega are the Fourier transform of our message signal or analog signal x of t, and p of omega is the Fourier transform of our sampling function, that is your p of. We had already stated that x of omega and p of omega are the Fourier transform of x of t and the sampling function p of t. Hence we can write xs of omega is equal to x delta of omega, obviously both are equal, is equal to 1 by 2 pi x of omega convolved with 2 pi by ts summation of n starts from minus infinity to infinity delta of omega minus n omega s. Here one should be clear about the Fourier transform of impulse train is equal to 2 pi by ts summation n starts from minus infinity to infinity delta of omega minus n omega s, obviously where omega s is the sampling frequency, angular sampling frequency. Since the Fourier transform I had written at this particular moment, Fourier transform of pt is equal to Fourier transform of this particular impulse train, that is analogous to or equivalent to 2 pi by ts summation n starts from minus infinity to infinity delta of omega minus n omega s. So with that we can have the spectrum of sampled signal, which has been given as xs of omega is equal to 1 by ts summation of x of omega minus n omega s. This spectrum has get shifted. So this particular figure shows the overall spectrum of our sampled signal. If we observe this particular figure properly, then we can conclude that spectrum will get replicated from minus infinity to infinity. Same spectrum, obviously same spectrum will get replicated from minus infinity to infinity, and in frequency domain or the sampled signal will be having this sort of spectrum only, and from this spectrum we have to reconstruct our analog signal back. How are we going to do that? We'll discuss later. We cannot use ideal sampling or impulse sampling because we cannot generate the impulse train practically. Obviously zero width pulse, to generate zero width pulse in laboratory, it is not feasible. So we generally do not use ideal sampling or impulse sampling in general. There is one more reason. Suppose by some means if we have generated a short duration pulses, then obviously the energy or power of that pulse will also be very low, and if we're going to use them for transmission purposes, obviously there is a noise that will going to add up in the amplitude due to additive nature of noise. So it will going to reduce signal to noise ratio significantly. So in communication purpose we generally do not use impulse sampling. So moving towards the next sampling method, which is our natural sampling. So natural sampling is similar to impulse sampling, except that the impulse train is replaced with the pulse train of period ts, and the width of that pulse is tau. This particular figure represent your pt. The span of pt is minus tau by 2 to tau by 2, and the strength is 1. So this pulse equation is being given as pt is equal to summation starts from minus n starts from minus infinity to infinity p of t minus nts. It is a periodic pulse which is having the time period of ts. It means after every ts seconds this pulse will going to be repeated. So when we're going to multiply our input signal xt to the pulse train pt, we get the signal as shown below. This is what we have studied so far. This is the generalized sampling method in which input signal will get multiplied with the sampling function pt. So the outcome will be like this. We had already studied that in our natural sampling we'll be having the outcome in terms of varying pulse amplitude. So the output of the sampler is given as, again, xs of t is representing the sampler output, that is equal to x of t into p of t, which is nothing but your sampling function. So by putting the values of pt, we have xt into summation starts from n is equal to minus infinity to infinity p times of p of t minus nts. This is showing the repetitive pulse. Let us say this is our equation number 1. Since our sampling function p of t is a periodic pulse, so we can expand it in exponential Fourier series. The representation of p of t in exponential Fourier series is being given as p of t is equal to summation n starts from minus infinity to infinity c of n e to the power n j omega s t. This is generalized Fourier series expansion. What is c of n? Let us say this is our equation number 2, and c of n is equal to 1 by ts integration starts from minus ts by 2 to ts by 2 pt e to the power minus n j omega s t dt. This is what the value of c of n, and when we're going to evaluate this particular integral, the outcome turns out to be 1 by ts p of n omega s. So now putting the value of this 1 by ts p of n omega s in this particular second equation, what we're going to have is p of t turns out to be, n starts from minus infinity to infinity, 1 by ts p times of n omega s e to the power n j omega s t. Obviously I suggest that all those mathematics you should do on paper, so that you will get a better idea about what we're going to having in this particular lecture. So this again turns out to be, we're going to take 1 by ts apart from this summation series, or before this summation series, 1 by ts n starts from minus infinity to infinity p of n omega s e to the power n j omega s t. Simply we are taking this 1 by ts outside of this summation. Now putting the value of pt in equation number 1, we have xs of t is equal to xt multiplied by sampling function pt, and by putting the value of this pt, we'll get xs of t is equal to xt into 1 by ts summation n starts from minus infinity to infinity p of n omega s e to the power n j omega s t, which is equal to 1 by ts summation n starts from minus infinity to infinity p of n omega s x of t e to the power n j omega s. We did nothing, we just taking x of t to inside this summation series, as each and every component of this summation series will get multiplied with this xt. So this is what we're going to have. So now to get the spectrum of the sample signal, let us again take the Fourier transform on both sides. Then what we're going to have, Fourier transform of x of t, xs of t is equal to Fourier transform of this complete equation, 1 by ts summation starts from n starts from minus infinity to infinity p of n omega s x of t e to the power n j omega s t, which turns out to be 1 by ts. By taking this 1 by ts out of the Fourier transform, summation n starts from minus infinity to infinity p of n omega s, this complete portion, and the Fourier transform of x of t e to the power n j omega s t. Since this is already in the frequency domain, so we just took out from our Fourier transform. So now according to the frequency shifting property of Fourier transform, we have Fourier transform of x of t e to the power n j omega s t turns out to be x of omega minus omega s. So spectrum is get shifted with the frequency of omega s. This is what the shifting property of Fourier transform in the frequency domain. So hence we can say that Fourier transform of sampled version of x of t is equal to 1 by ts summation n starts from minus infinity to infinity p of n omega s into Fourier transform of x of t e to the power n j omega st. Hence the spectrum of the sampled signal is being given as xs of omega is equal to 1 by ts summation n starts from minus infinity to infinity p of n omega s into x of omega minus omega s, the shifted version of this x of omega. So what this shifting property is actually saying that the complete spectrum of x of t will get shifted with the frequency omega s. This is what it is showing. So this is the actual spectrum of our sampled signal. Again we can understand that this is actually the composite spectrum of our pulse as well as our analog signal, and it is get replicated throughout the frequency interval from minus infinity to infinity. So we'll be left with this particular spectrum from which we have to retrieve our analog signal back. So with the help of low pass filter, what we can do is, or how we're going to reconstruct our message signal from this particular spectrum, we'll see. So now third type of sampling method is our flat top sampling. So during the transmission, noise is introduced at the top of the transmission pulse, which can be easily removed if the pulse is in the form of flat top. Why we are making this statement? Suppose due to additive nature of noise will get added on the top of our transmitted signal, and transmitted signal, if it is flat top, then obviously we can predetermine the level of sampled pulses, and whatever excessive amplitude we are getting from that predetermined level of pulses, that will be a noise and we can easily reject them. So the signal to noise ratio will get improved at the receiving side. So this is just a statement. As of now, if you don't understand it, let it be. In upcoming lecture we'll analyze it more properly. So the top of the samples are flat, that is they have constant amplitude, hence it is called the flat top sampling or practical sampling. Next, what is happening in our flat top sampling? Again we're going to have some analog signal which is represented by xt, which is get multiplied with the sampling function p of t, which is nothing but a periodic pulse train. Again pulse width of tau, and ts is the, obviously capital Ts is the sampling period. So the outcome will be this sort of stuff, which is the outcome of flat top sampling. So mathematically we can consider the flat top sampled signal is equivalent to the convolved sequence of the pulse pt and the ideal sampling signal x delta of p. This is your pt, pulse strength is 1 and duration is of tau, starts from minus tau by 2 to tau, into the impulse sample signal. So the outcome will be like this one. Obviously there is a mistake, it has not to be the multiplied sign, it has to be a convolution sign. So xs of t, that is the sampled version of x of t, will be equal to pt convolved with x delta of t, where x delta of t represent the impulse sampling of our input signal or analog signal. So we can write that xs of t is equal to sampling function pt convolved with this impulse sampled, this impulse sampled sequences, which is equal to k starts from minus infinity to infinity x of kts delta of t minus kts. Okay, so the convolution of these two signals will give me the outcome of flat top sampling. So now applying the Fourier transform, what we're going to have is xs of omega, which is again the Fourier transform of xs of t, is equal to p of omega x delta of omega. As we had already discussed, and we should know that convolution in time domain will become the product in frequency domain. So s of omega is equal to p of omega into 1 by t of s summation n starts from minus infinity to infinity x of omega minus n omega s. We had already devised up in impulse sampling what will be the frequency spectrum of this x delta of omega. So what we are left with, xs of omega is equal to 1 by ts, n starts from minus infinity to infinity, p of omega x of omega minus n omega s. Obviously this particular figure shows the frequency spectrum of our flat top sampled signal. This particular frequency spectrum is the composite spectrum of our pulse p of omega and x of omega. As this is infinite summation, so we can say that the same spectrum will get replicated from minus infinity to infinity, and from that spectrum we have to recover our analog signal back. So here p of omega and x delta of omega are the Fourier transform of pt and x delta of t respectively. So now the question arises, how we are going to reconstruct our signal back from the sampled signal. Obviously we are not going to go through the greater details how we are going to reconstruct our message signal back, as for reconstruction we generally using our interpolation method or zero order hold circuitries. We are not going to go into greater details of that, but obviously if after sampling we are getting some spectra of our signal, so from that spectrum how we are going to reconstruct our signal back. So here we are considering three cases in which xs of omega shows the spectrum of our sampled signal. So in first case we'll be having this spectra. Obviously these are non-overlapping spectrum, or what we are doing is we are taking sufficient number of samples, means number of samples is greater than or equal to twice of fm. So if we are imposing that condition, we'll be getting sampled signals separated by some amount of frequency ranges. If we take exactly twice of fm number of samples, then what we'll get in frequency domain, we'll getting non-overlapping sequences of frequency spectrum, but there is no frequencies left in between them. And if we are taking lesser number of samples, that is if we are taking lesser than twice of fm number of samples, then we'll getting this sort of spectrum, which is your overlap. So with this spectrum only we have to recover our input signal back. So what we're gonna do is we use a low pass filter with a transfer function h of omega. If we pass this particular spectrum by this low pass filter, we'll only left with this spectrum portion, which is in time domain nothing but your input signal or analog signal. So if we consider the above two cases, I mean this one and this one, we do not have any overlapping region, but if the sampling rate is lesser than twice of fm, we'll getting these overlapping region. And if we try to pass this particular signal from this particular low pass filter, what we'll get is we'll get distorted signal outcome. So due to this distortion, we are not in a state to recover our signal back. So for proper reconstruction of our signal, the sampling frequency or sampling rate should be greater than or equal to twice of fm. So for proper reconstruction, we want that there should be no overlapping in the frequencies, so that we could get our signal distortion free and we can appropriately recover it. So then next question is, what is this frequency value? Obviously this is your omega s and this is your omega m, then this frequency will be omega s minus omega m. So for proper reconstruction of our analog signal with the help of low pass filter, this frequency omega s minus omega m should be greater than omega m. Only then we are in a state to avoid the overlapping of the frequencies or overlapping of the spectrum. So we can say that omega s minus omega m should be greater than omega m. So this condition imposes omega s should be greater than or equal to twice of omega m, which is nothing but the Nyquist criteria for the reconstruction of sampled signal. Omega s should be greater than or equal to twice of fm, or if we are talking about in terms of linear frequency, the sampling frequency f of s should be greater than or equal to twice of fm. Obviously omega m is our angular frequency, which is equal to 2 pi fm. Omega m is equal to 2 pi fm and omega s is equal to 2 pi fs. So what does these overlapping regions signifies? Due to this overlapping, we'll getting distorted signal outcome. So this effect where frequencies will get overlapped due to undersampling, this effect is called the aliasing. So due to aliasing, we are not in a state to extract our signal back or recover our signal properly. So what is this aliasing? Aliasing refers to the phenomena of high frequency component in the spectrum of a signal seemingly taking the identity of lower frequency in the spectrum of its sampled version. Obviously, if we consider this particular figure, what we are seeing that the highest frequency component of this particular spectrum will going to get overlapped with the lower frequency component of this particular spectrum portion. So due to this overlapping, we'll get or we'll recover distorted signal. This effect is known as aliasing. So undersampling version of massive signal is the major cause of aliasing. It means if the sampling rate is less than twice of fm, then aliasing occur. It is worth to mention here that any time limited signal cannot be band limited and any band limited signal cannot be time limited. Since all the signals are more or less time limited, it means they cannot be band limited. What do you mean by this particular statement is, we had already studied that the bandwidth requirement of impulse is infinite. It means impulse is a time bounded signal. If signal is time bounded, then its frequency requirement will become infinite, and if the signal is time unlimited, then only its frequency will get limited. For example, our sync pulse starts from -infinity to infinity and it is having some specific bandwidth. Obviously we can quantify the bandwidth of our sync pulse. So if our signal is time limited, then it will become unlimited in frequency bands, and if our signal is band limited, then it will become time unlimited. Hence we must pass most of the signals through a low pass filter before sampling in order to make them band limited. This is called the anti-aliasing filter, which is nothing but a low pass filter, and it is typically built into the analog to digital converter. So obviously sampling theorem is only valid for band limited signal. If our signal under consideration is not band limited, then first we have to make it band limited so that sampling theorem will get applicable. So distortion will occur if the signal is band limited. Obviously we have seen that due to aliasing effect, distortion will occur and will not in a state to recover our analog signal back. So when the signal is sampled, we refer to this distortion as aliasing. If sampling rate is less than twice of fm, then overlapping in frequency band will going to occur and distortion will occur when we're going to recover our massive signal back, obviously from the sampled signal. So these are the references. Thank you very much for your patient hearing.